When people talk about running a large language model locally, the first question is usually, how big is the model? Fact. Is it 7 billion parameters? 32 billion? 70 billion? Then we look at the file size, compare it with the amount of VRAM or unified memory in the computer, and assume we already know whether the model will run. A 40 gigabyte model should fit inside 48 gigabytes of memory. Simple, right? Not always. Because the model file is only one part of the memory equation. In some situations, the thing consuming most of your memory is not the model itself. It is everything the model creates while it is running. And this is why a model can load successfully, generate a few words, and then suddenly crash when you paste in a long document. It is also why a model that works perfectly for one user may run out of memory when several users connect at the same time. So today, I want to explain where all that extra memory goes, why long context can become surprisingly expensive, and why checking the model size alone can give you a completely wrong idea of what your hardware can handle. Let's start with the most obvious part, the model weights. The weights are basically the stored knowledge of the model. They are billions of numbers learned during training. When you download a model, most of the file you are downloading consists of these weights. If a model has 70 billion parameters and each parameter is stored using 16 bits, the raw weights alone require roughly 140 gigabytes. Quantize those weights to 8 bits and the number drops to around 70 gigabytes. Quantize them to 4 bits. And you may get somewhere around 35 to 40 gigabytes after accounting for additional metadata and quantization overhead. That is the number most people focus on. And to be fair, for small models and short conversations, the weights usually are the biggest memory consumer. But once the model begins processing a long context, another major component starts growing. That component is the KV cache. KV stands for key and value. These are intermediate results created inside the attention layers of a transformer. When the model reads your prompt, it does not want to recalculate the entire conversation from the beginning every time it generates a new token. That would be extremely wasteful. Instead, it stores certain attention information from previous tokens in memory. That stored information is the KV cache. You can think of the model weights as a fixed library, and the KV cache as the model's working notebook. The library stays roughly the same size no matter what question you ask, but the notebook gets larger as the conversation gets longer. If you send a short prompt, the notebook is small. If you paste in an entire book, a large code base, or hundreds of pages of documents, the notebook becomes much larger. And unlike the model weights, which are usually heavily quantized, the KV cache may be stored at a higher precision. Your model might use 4-bit weights, but its KV cache could still use 16-bit values depending on the runtime and configuration. That means a small quantized model can still consume a surprising amount of memory during long context inference. Imagine that you load a model and see that it uses 20 gigabytes of VRAM. Your GPU has 24 gigabytes, so you think you have 4 gigabytes left. With a short prompt, everything works. Then you increase the context window to 32,000 tokens. Memory usage rises. You push it to 64,000 tokens. It rises again. At 128,000 tokens, the model may no longer fit, even though the model weights have not changed by a single byte. This is one of the most important ideas to understand. Context length is not free. A model supporting a 180K context window does not mean your computer can actually use all 180,000 tokens comfortably. It only means the architecture and software are capable of addressing that context length. Whether your machine can handle it depends on the model architecture, the KV cache format, the number of layers, the number of attention heads, the batch size, and the memory available. Some newer models use techniques such as grouped query attention or multi-query attention to reduce KV cache usage. Instead of storing a completely separate set of keys and values for every attention head, multiple heads can share them. This can make long context inference much more memory efficient. But the basic rule still holds. The more tokens the model remembers, the more working memory it usually needs. And the KV cache does not just affect maximum context length. It also becomes a major issue when serving multiple users. Suppose you are running one model for yourself. There is one conversation and one KV cache. Now suppose you are hosting the same model as an API for 10 users. Each user has a separate prompt, a separate conversation history, and usually a separate KV cache. You do not need 10 copies of the model weights. Those can be shared. But you may need 10 sets of active inference state. This means the model itself could fit easily into memory, while the concurrent requests consume everything that remains. That is why production inference systems care so much about batching, cache management, prefix sharing, request scheduling, and memory paging. The challenge is not simply loading the model, the challenge is keeping many active conversations alive without wasting memory. Batch size also changes the equation. If I process one prompt at a time, memory usage is relatively low. If I process 8 prompts together, the GPU can often work more efficiently because it has more parallel work to do. But those 8 prompts also require more temporary memory and more KV cache. So there is always a trade-off. A larger batch can improve throughput, meaning the server generates more total tokens per second. But it may reduce the maximum context length or the number of users that can fit into memory at once. This is why a benchmark saying a GPU produces 200 tokens per second can be misleading. Was that one user generating at 200 tokens per second? Or was it 20 users generating 10 tokens per second each? Those are completely different experiences, even though the total throughput is the same. There is another category of memory that people often overlook: temporary activations and workspace buffers. As data moves through each layer of the model, the GPU creates intermediate tensors. Some exist only for a very short time, but they still need memory while the computation is happening. Attention kernels, matrix multiplications, normalization layers, and other operations may also request temporary workspace. The amount depends on the framework, the backend, the hardware, the selected kernels, and the shape of the input. This is one reason two inference programs can use different amounts of memory while running exactly the same model. You might load the same quantized model in two applications and find that one uses 18 gigabytes while the other uses 21 gigabytes. That does not necessarily mean one of them is broken. They may use different attention implementations, different cache formats, different memory allocators, or different levels of pre-allocated workspace. Some runtimes reserve a large memory pool at startup to reduce fragmentation and avoid repeatedly allocating and releasing GPU memory. So the memory shown as used may not all contain active model data. Some of it may simply be reserved for future operations. Memory fragmentation can also create strange failures. You might technically have 2 gigabytes free, but the program needs one large continuous block of memory and cannot find it. The total free memory looks sufficient, yet the allocation fails. This is similar to having enough empty seats in a theater, but not enough seats together for a group that wants to sit in the same row. So when a model requires 22 gigabytes, a 24 gigabyte GPU may still be uncomfortable. You need some headroom for the cache, temporary buffers, the operating system, the display, the driver, and unexpected memory spikes. Now, everything I have described so far applies mainly to inference, which means using a trained model to generate output. Training is a completely different level of memory consumption. During training, you do not only store the model weights, you also store gradients, which tell the optimizer how each parameter should change. Depending on the optimizer, you may also store multiple additional values for every parameter. Atom, for example, typically maintains extra momentum and variance statistics. Then you have activations from the forward pass that must be kept for the backward pass. So a model that needs 140 gigabytes for its 16-bit weights could require several times that amount during full training. The weights may not even be the largest part anymore. Optimizer states, gradients, and activations can dominate the memory budget. This is why techniques such as gradient checkpointing exist. Instead of storing every activation, the system stores fewer of them and recomputes some values during the backward pass. That saves memory, but it increases computation. Once again, we are trading speed for capacity. Fine-tuning methods such as LoRA and QLoRA are popular partly because they avoid updating every parameter in the model. The original model weights can remain frozen while the training process updates a much smaller set of adapter parameters. This dramatically reduces the memory needed for gradients and optimizer states. But even with QLoRA, the base model is not the only thing using memory. You still need activations, adapter weights, optimizer data, and temporary buffers. So when someone says, this model is only 40 gigabytes, so it should train on a 48 gigabyte GPU, that conclusion is usually wrong. It might fit for inference. Training is another story. There is also a difference between dedicated GPU memory and unified memory. On a traditional GPU, VRAM is a fast, dedicated memory pool located close to the GPU. On an Apple Silicon machine or another unified memory system, the CPU and GPU can access the same memory pool. That can make it possible to load models much larger than the VRAM available on a typical consumer graphics card. But unified memory is still shared. The operating system needs memory. Your browser needs memory. The inference application needs memory. The model weights, KV cache, and temporary buffers all come from the same pool. So a Mac with 64 gigabytes of unified memory does not provide 64 gigabytes entirely to the model. The amount actually available may be several gigabytes lower, and the system may begin compressing memory or swapping data to the SSD before you reach the physical limit. The model may continue running, but performance can collapse. This is another important distinction. Fitting is not the same as running well. A model can technically fit by offloading some layers to system RAM or even using SSD batch virtual memory, but if the processor constantly moves data between storage, RAM, and the GPU, token generation can become painfully slow. Memory capacity determines whether the workload can exist. Memory bandwidth and compute performance determine how quickly it runs. And context length affects both. A long prompt not only increases KV cache memory, it also requires the model to process more tokens during the initial prompt evaluation stage. You may notice that after pasting a long document, the model pauses for a while before generating the first word. That delay is often called prefill time. The model must process the entire input and build the KV cache before normal token-by-token generation begins. Once the cache is built, generation may become faster. But as the context grows, each new token may still require attention over a larger amount of stored information. Some architectures and attention methods reduce this cost, but there is no completely free infinite memory. So when I evaluate whether a computer can run a model, I do not just ask how large the model file is. I ask what precision the weights use. I ask how long the context will be. I ask how many requests will run at the same time. I ask whether the KB cache is quantized. I ask whether the program is using full GPU acceleration, CPU offloading, or unified memory. I ask how much memory the operating system and other applications will consume. And most importantly, I leave headroom. If a model barely fits with an empty prompt, it does not really fit for practical use. The moment you open a long conversation, load a document, increase the batch size, or start another application, you may cross the limit. This is why two people with apparently similar hardware can report completely different results. One person is testing a 5-word prompt with a 2000 token context. The other is loading a 100-page PDF with a 64,000 token context. They are not really running the same workload. The model name is the same, but the memory demands are completely different. So the next time you see someone say, "This model only needs 20 gigabytes of memory," treat that number as the beginning of the conversation, not the final answer. 20 gigabytes may describe the weights. It may not include the KV cache. It may not include temporary buffers. It may not include multiple users. It may not include the operating system. And it definitely does not tell you how much memory the workload will need during training. The model is the thing we can see. It is the file we download, the number in the model name, and the item everyone compares. But the hidden memory costs often determine whether the experience is smooth, slow, or completely impossible. In many real-world situations, the biggest memory problem is not storing what the model knows. It is storing everything the model is trying to remember while it works.